in high school. This is Mr. Aiden, and it is 9.1 electrostatics, guys. We're going to be going out of the macro scale here. We've been dealing with the macro scale, dealing with Newtonian mechanics, and we've been dealing with fluid mechanics and everything on the macro scale. We're going to be going to the subatomic scale now. We're going to be going down to electricity and magnetism here, and this is the great precursor, which is electrostatics. But before I begin there, I got to make a little analogy, and we're going to start with our main man, Isaac Newton. And of course, Isaac Newton has his trusty apple, and of course, when he drops that apple, it is going to have a force of gravity, okay, and it's going to accelerate downwards at 9.8 meters per second squared. We know that. Okay, and why is it gonna fall downwards? Why do we have this force of gravity? Well, we're gonna look at an even more macro scale. We're gonna look at the entire Earth. And Sir Isaac Newton, a little bit bigger than we expect, sitting on top of the Earth. And what's gonna happen is he drops that apple, and it has a force of gravity pointing down. Now, what happens if Isaac Newton is on the right-hand side of our Earth? Okay, the apple's still gonna fall down, isn't it? But to our perspective, it's falling to the left, okay? But if he's upside down, if he's on the bottom side of the Earth, guess what? It still falls down. To our frame of reference, it looks like it's falling up. But you can see the force of gravity always points where? Inwards, towards the surface of the Earth. And we can say that there is a gravitational field all around the Earth, right? It doesn't matter where you're staying on the Earth, things are going to fall down towards the Earth, which means there's a gravitational field, which produces what we call the force of gravity. Okay, a gravitational field produces the force of gravity. Now, I'm going to take us from the macro scale, I'm going to take us from the human, and I'm going to come all the way down to what we call the subatomic scale. All the way past all these different things, past DNA, past phospholipids, past the alpha helix, all the way down to an electron. Okay? And a positron and things like that, down to the subatomic scale. Okay, and so let's come back to our charges. Okay, now we're on the subatomic scale, and we have a negative charge and we have a positive charge. And the funny thing is, a negative charge looks very similar to the Earth, which means the negative charge has what we call not a gravitational field; it actually has what we call an electric field. And that electric field is always pointing into the negative, into a negative charge. But if we have a positive charge, it's going to be pointing out of a positive. So negative charges, the electric field lines or the electric field strength is going to be pointing in. Positive charges, the electric field is going to be pointing out. Which means if we have a positive sitting right next to a negative, you can see where our electric field lines are going. Out of the positive and into the negative. They never cross. They're getting stronger and stronger the closer you get to the charge, okay? And you can see what happens if we have two positives, or in this, we could have two negatives even, and it would look very similar. There's this void, isn't there? The electric field lines will repel each other. And you can see this is why opposite charges attract and like charges repel each other. It is due to their electric field strength. Let me come back to a simulation here. Here I have a positive charge, okay, and you can see this positive charge. Let me turn off the electric field lines. You can see this is a little sensor that shows the electric field strength, okay, and my electric field is going out of the positive, and you can see as I get closer and closer, what happens to that strength? It gets greater and greater and greater. And so it's always going to go out of the positive. It doesn't matter where I'm at, it's out of the positive. Okay, you can see that with our electric field lines, out of the positive. Okay, but if I replace this with a negative charge right there, okay, where's my electric field strength going to be going? Into the negative. It doesn't matter where it's going to be out of the positive and into the negative. If I put a positive right here, you can see, I'm going to take this sensor off, you can see I'm going out of the positive, my lines are going out of the positive and into a negative. But if I have two of the same charges, they will repel each other. Okay, they will repel each other, and that's going to bring us back to our little simulation right here. Okay, these electric field lines produce an electric force, just like the gravitational field strength around the Earth produce a gravitational force. Okay, here we're just going to take a look at the blue, the negative charge. This blue negative charge, he's going to be feeling an electric force towards the red positive charge, because we know opposite charges attract. That's my wife and I, right? We're opposites. she's really attracted to me, okay? Opposite charges attract, whereas like charges do what? They repel, okay? And there's a nice easy equation for the electric field strength, and it is KQQ over R squared. K is a constant, because constant begins with the letter K, and it's 9 times 10 to the 9th, 99. Really easy on your calculator. Q are the charges. Q is the one charge, the blue charge. Q would be the other, the red charge. And R squared would be their distance squared, their distance away. Okay? Now, what would happen if I had another positive charge down here? Well, we're going to take one at a time. And this blue will be also attracted to this other charge. Okay? He's attracted to the top red charge. He's attracted to the bottom red charge, which means together, you can see if we add both these vectors up, there's a net force propelling this negative blue charge to the right. And you can see if I take this guy and I add both those vectors up, you can see the y's end up canceling out. It's the x's that add up together. You can see again the y's cancel out. One's going up, one's going down. The x's add together. Okay? Guys, that is our introduction to electrostatics. I hope this helped, and we will get going on in class with this. Thanks, guys. Bye.